Hello, welcome to a new chapter. Let's do exercise 3. It tells us that we have a real scalar field given by this Lagrangian density. Verify that the action has the symmetry blah blah blah, where V is a real constant, and find the conserved current corresponding to this symmetry. Well, the first thing to see is that as this symmetry is defined, it's finite. Why? Because B, this parameter, can be, for example, 174 or 12, so it's valid for any B. This is the reason why this transformation is finite. But the thing we need is an infinitesimal transformation, which means close to the identity. But what is the identity in this case? As you can see, the identity is equivalent to choosing B equal to 1, because we would have that x would be x and phi would go to phi. This is the identity. So we can translate close to the identity by means of 1 plus something. This something must be an infinitesimal quantity, which implies that epsilon squared equals 0. This means x0 going to be x0, x1 going to be x1, etc. Summarizing, we have x mu going to be x mu. So the variation of x mu will be bx mu minus x mu equals b minus 1 times x mu. But looking at this is epsilon x mu. So regarding the scalar field, the transformation is phi prime equals 1 over b times phi, but b equals 1 plus epsilon. And if we do a Taylor expansion, you can check that this is 1 minus epsilon plus epsilon squared terms, and we can make this quantity equals 0. This is a simplified rule. So approximately this is 1 minus epsilon times phi. So the variation of the scalar field is phi prime minus phi by definition. If you substitute, you will obtain 1 minus epsilon phi minus phi equals minus epsilon phi. Okay. Another thing we are going to need is the variation of the partial derivative of the field. So let's do an example in one dimension to see how it works. For example, imagine you have f of x, but tilde, which means the transformed function, which will be 1 over b times f of x. Okay, now we're going to take the derivative with respect to the transformed variable on both sides of the equation. Remember, this is the transformed variable. In the right-hand side, we will have 1 over b times the derivative of f with respect to x, tilde. So applying the chain rule, we will have dx tilde, df dx, and this is, knowing that x tilde equals bx, this implies that this is 1 over b. We will have 1 over b squared times df dx equals, but b equals 1 plus epsilon, so 1 over 1 plus epsilon squared df dx. Let's do a Taylor expansion again, and you can check that this is 1 minus 2 epsilon plus epsilon squared terms. So this is equal 1 minus 2 epsilon times df dx. So this is equal to this. So if we define the variation of the derivative of the function, the derivative in the tilde world minus the derivative in a world without primes, looking at this, we will have 1 minus 2 epsilon df dx minus df dx. This one and this derivative cancels out, and the final result is minus 2 epsilon df dx. So the variation of the derivative is minus 2 epsilon df dx. We will repeat the calculations, but in 4 dimensions. This is the derivative in the tilde world. This will be the partial derivative with respect to x tilde mu of the transformed function, that is 1 over b times the function. Let's apply the chain rule times the partial derivative with respect to x beta with respect to x tilde mu times the partial derivative 5 with respect to x beta. This is Kronecker delta, delta beta mu, because only if beta and mu are equal, then it will give us something different from 0. But remember, the relation between x and x tilde is 1 over b. So we will have 1 over b squared, and let's sum the beta index. So we will put mu instead of beta. So we have partial mu phi of x. So the variation of the partial derivative will be this minus the partial derivative, the ordinary partial derivative. And this will give us, oh, by the way, 1 over b squared, remember, is 1 minus 2 epsilon times the partial derivative. So let's replace the result. 1 minus 2 epsilon minus 1 due to this minus 1 times the partial derivative of 5. 1 minus 1 is 0, so the final result is minus 2 epsilon, the partial derivative. The same result than before. Now we need to test if this is a symmetry or not, namely if the action is invariant under this transformation. And as you know, this will be a symmetry if the symmetry test is fulfilled. But remember, the symmetry test is this large equation. In our case, we only have one field. Therefore, there is only one value for this index, for the index A. So we can delete this index and this one too, because we are working with a scalar field. Now let's make a first attempt, assuming that omega is 0. Let's see if it works. Let's delete it. Let's calculate this first expression, 1/2 partial mu phi plus 1 over 4 factorial times phi to the 4. And now let's calculate the partial derivative of the variation. But the variation is epsilon x mu. We can factor out epsilon because it's a constant. And remember, this is a sum. I mean, partial 0 x0 plus partial 1 x1 plus blah 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 up to 3. And then this is 1 plus 1 plus 1 plus 1 equals 4 epsilon. Next, plus the partial derivative of L with respect to phi, but this is the only term that depends on phi, so it's 1 over 3 factorial lambda phi to the 3rd. So this is done, and now the variation of the field, but this is minus epsilon phi. Okay, now the partial derivative of L, but remember this is partial mu phi with index mu upstairs. Remember, we saw this in the first exercise. The next term is this, but we've calculated a few minutes ago. So let's substitute minus 2 epsilon partial mu phi. And this is 0 because there is no explicit dependence on x in the Lagrangian density. The Lagrangian density in our case only depends on the derivatives or the fields, but not in the space-time coordinates. Okay, let's expand this expression a little bit. This times this is 2, epsilon partial mu phi plus 1 over 6 phi to the 4 epsilon minus epsilon lambda phi to the 4th over 6. Oh, by the way, I forgot to write lambda here, sorry. This lambda from here, okay. Okay, the last term is minus 2 epsilon partial mu phi partial mu phi. And let's see, this term cancels out with this term and this with this. So this is equal to 0. This implies that the integral of 0 is 0, of course, if we are talking about a finite region of space-time. So, confirmed, this is a symmetry of this Lagrangian. Okay, now is the turn of the conserved carbon. Remember that Santi deduced it for you in theory class. Okay, but remember omega is 0 in our case. And remember also that A takes only one value, so we can delete it. So let's calculate the first term. As you for sure remember, this is partial mu phi. Delta phi is minus epsilon phi plus delta mu nu. The Lagrangian density minus this derivative is the same that before, so partial mu phi times partial nu phi times the variation of x, but this is epsilon x mu plus 0. Let's factor out epsilon and let's write this minus to the left and the field phi also. So remember, we can read off this epsilon because if something is constant, the product of two constants is also a constant. So to be more precise, we should define j mu as a constant times this expression. Namely, j mu is proportional to this expression. The proportional constant is epsilon, of course. Let's substitute the Lagrangian density. Oh, sorry, I forgot to change. Sorry, this mu index is in fact new. This new. Sorry. Now we're happy. If you wish, we can change these indices because there is another mu in the expression in order to avoid possible confusions. Now we are happier. Okay, now we will do exercise 4. It tells us to consider a theory with two fields that don't interact with each other, phi1 and phi2. Here's the Lagrangian, and a new field and its transposed is defined. Show that this Lagrangian can be written in terms of the new field. So let's start with the derivative of the field. Then, on the other hand, we calculate the derivative of the transposed field. Okay, so now we multiply the derivative of the transposed field by the derivative of the non-transposed field. We can see now that the scalar product of these terms returns the original kinetic term from which we started. Now the mass term, the transposed field multiplied by the original field, and again we make the scalar product. By multiplying by m squared, we recover the remaining term. So, subtracting these two terms, we can recover the original Lagrangian. Okay, now check that the Lagrangian is invariant under this internal rotation. One has to be careful because it's a finite rotation, that is, the angle is finite. So now we define the transformed field as the rotation matrix times the untransformed field. Now we transpose the equation and therefore the order of the terms has to be reversed, with its transpose, of course. So if we multiply these two expressions, we get this. But remember that a rotation matrix fulfills that the transpose matrix multiplied by itself is equal to the identity. These kind of matrices are known as orthogonal matrices, and if you wish, we can easily check this. We recover the product of the transposed field multiplied by itself. Let's now check the derivative of this equation. And due to the fact that the R matrix is constant, it can be taken out of the derivative. If we do the same in this equation, the transposed rotation matrix can also come out, but we must be careful because the transposed rotation matrix comes out on the right side. The reason is that it's a row vector that is being multiplied by a matrix, and the same order must be maintained. Again, we multiply one term by another. We get the identity. Therefore, we recover the original kinetic term. So A and B implies that the transformed Lagrangian is just the original Lagrangian. So this is a symmetry. Notice that there is no need to use the symmetry test condition because we are dealing with a finite transformation that leaves the Lagrangian invariant. Okay, let us continue with the exercise, and now we are asked to calculate the infinitesimal variation of this transformation. So in this case, we convert the angle into an infinitesimal quantity. The matrix will now be this expression. If we do a Taylor expansion, it becomes this. We eliminate the terms epsilon squared, and therefore we can express the rotation matrix as the identity plus something. That something will be epsilon multiplied by the matrix 0, -1, 1, 0. We call this matrix B, for example. So the infinitesimal variation of the field, defined as the transformed field minus the original field, will be this. This expression becomes epsilon times B times psi. Okay, now we're going to calculate the associated conserved current. So we copy the same formula as before, but I don't copy this piece of the expression because the variation of the space-time coordinates is 0 because there is no variation of x in the transformation. Moreover, it can be verified that if the transformation doesn't imply a change in the space-time coordinates, and in addition the global transformation leaves the Lagrangian invariant, then omega is 0. So these simplifications make our life easier. And now the index A is now relevant because in this context, it's a kind of two-component vector. This implies that actually the conserved current is a sum of two terms, one with the index equal to 1 and the other with the index equal to 2. And this is phi 1 and phi 2, of course. This is the first option we can think of, but there is an alternative. It consists of considering as if the transposed field and the non-transposed field act as independent fields. This is just a mathematical trick because, of course, both the field and the transposed field are dependent on each other in a strict mathematical sense. But at the level of calculation, such things work, and sometimes it's easier to calculate it in that way. To calculate the first derivative, we look at the Lagrangian and write the term that multiplies the partial derivative. And to calculate the other derivative, we can re-express the Lagrangian in this other way. Remember that the Lorentz scalar product can be written in this way, but the position of the indices can also be exchanged, so to say. This allows us to calculate easily the derivative. On the other hand, the variation of the field, as we have seen before, is epsilon b times psi. Now we calculate the transposition of that variation, and this is the variation of the transposed field equals epsilon psi transposed times b transposed. So this variation is epsilon psi b transposed. Okay, before we continue, we have to check if we have placed the terms correctly in the right order. Psi is a column vector, b is a 2 by 2 matrix, and the transposed derivative is a row vector. So this term is going to give a number, okay? However, in this case, we have a matrix, a row vector, and a column vector, and this doesn't give a number. This may seem like a serious problem, but it's not. We simply have to change the order, and that's it. Okay, as we did in previous exercise, we eliminate epsilon. B is an anti-symmetric matrix, so the transpose is itself with the opposite sign. Okay, let's check that this result coincides with the one we would have obtained with the first method. We can substitute directly the expression of the field, phi1 and phi2. Sorry, this is a minus sign, sorry. Okay, if we multiply it, we'll give. And these two terms are the same, and these two terms are the same also. So we get this parenthesis twice. And that's it. Thank you very much for watching this video. This is the last video of the semester, so I wish you the best of luck for the exam, and I'm sorry that we couldn't have a face-to-face class, which is certainly always much better than being locked up in our houses. So thank you all very much, and good luck in the exam and in your lives. Goodbye.
Mod fx squared dx. So please finish Percival by next time. I know many of you had this as undergraduates, but it won't hurt to brush up. Thank you, Stephen. I also put an advanced Fourier system on the main hallway chalkboard. And I'm hoping that one of you might prove it by the end of the semester. And the person to do so will not only be in my good graces, but also go on to fame and fortune by having their accomplishment recorded and their name printed in the auspicious MIT Tech. Former winners include Nobel laureates, Fields Medal winners, renowned astrophysicists, and lowly MIT professors. Well, that's all. If you have any questions, I'm sure that Tom has the answers.